What if the greatest miracle in the cosmos is not the fire of a newborn star or the silent dance of a trillion galaxies? What if the most profound, the most unsettling, the most improbable wonder is simply nothing? Or rather, a perfect, exquisite and terrifying balance between everything and nothing at all. We live our lives on a knife's edge. Every action, every choice and negotiation between success and failure, order and chaos. We instinctively understand the nature of equilibrium. A spinning top, wobbling precariously, is a battle against gravity, a fleeting victory of motion. A perfectly balanced stone sculpture seems to defy the very laws of physics, a moment of serene impossibility held in suspended animation. These moments of balance are rare, beautiful, and above all temporary. The slightest nudge, the faintest breath of wind, and they collapse back into the mundane. Chaos is the default state of things. Order is the fragile exception. Now take that intuition, that gut feeling about the universe's preference for disorder, and cast your gaze across the entire expanse of space-time. Out here in the grand arena of reality, we see a spectacle of such majestic order that it should by all rights be impossible. The cosmic web, that luminous tapestry of galactic superclusters, stretches for billions of light years, a filigree of shimmering light and profound darkness. It is a structure of breathtaking complexity, yet one governed by an underlying, almost serene uniformity. It appears stable, it seems permanent. But this cosmic tranquility is the grandest of all illusions. Our universe, this vast and sprawling home of ours, is balanced more precisely than any spinning top, more delicately than any sculptor's masterpiece. It is balanced on a point so fine a fulcrum, so narrow, that it defies all logic, all probability, all of our deepest intuitions about how reality should work. This is not a story about the things you can see, the stars, the nebulae, the celestial fireworks. This is a detective story about the very stage on which they perform. It is the story of the shape of space itself, and the discovery of a cosmic coincidence so extreme it forced us to rewrite the history of creation. This is the flatness problem. To understand the depth of this enigma, you must first unlearn what you think you know about space. We imagine it as a black, empty void, a passive backdrop for cosmic events. But Albert Einstein revealed a far more dramatic and powerful truth. Space-time is not a stage. It is the principal actor. It is a dynamic, malleable fabric, a four-dimensional ocean that can be warped, bent, and stretched by the presence of matter and energy. Imagine a planet not as a marble rolling on a flat table, but as a heavy ball creating a deep well in a stretched rubber sheet. Gravity is not some mysterious force reaching across the void. It is the curvature of space-time itself, guiding objects along its contours. We are all at this very moment sliding down a gentle gravitational slope created by the Earth, a slope that holds us in place. The moon is forever falling into the valley created by our planet, moving just fast enough to constantly miss it in an eternal looping embrace. This is the core of general relativity. Matter tells space-time how to curve, and the curve of space-time tells matter how to move. It is the most elegant cosmic dance ever conceived. But if every star, every galaxy, every particle of dust bends the fabric of space around it, what about all of them together? What shape does the entire universe take when you account for every last atom and photon within it? The equations of relativity offer not one but three distinct possibilities for the ultimate geometry of our cosmos. Three cosmic destinies, each with profound and mind-bending consequences. The first possibility is a universe with not quite enough stuff in it. Its overall density of matter and energy would be too low to halt its expansion. In this scenario, the fabric of space-time would curve outwards like a saddle or a Pringles chip. This is what cosmologists call an open universe. In this reality, the rules of geometry you learned in school are broken. If you and a friend stood side by side and fired two laser beams perfectly parallel into the void, you would expect them to stay parallel forever. But in an open saddle-shaped universe, those beams would inexorably drift apart, diverging further and further as they traveled across the cosmic expanse, lost to each other for eternity. This geometry implies a bleak and lonely fate. An open universe is one that will expand forever, its galaxies rushing away from each other until the cosmos becomes a cold, dark, and unimaginably dilute graveyard, a state of ultimate entropy known as the heat death. It is a story that ends not with a bang, but with the quiet extinguishing of the last light. The second possibility is the exact opposite. Imagine a universe packed with just a little too much matter and energy. Its immense gravitational pull would overwhelm the outward momentum of the Big Bang. Here, space-time curves in on itself, forming a four-dimensional sphere. This is a closed universe, and in this cosmos, our laser beams would do something even stranger. Launched in parallel, they would begin to converge, drawing closer and closer over cosmic distances, until billions of light-years away they would eventually cross and meet. This spherical universe is finite, but it has no boundary, no edge. Like walking on the surface of the Earth, you could travel in a straight line forever and never reach an end. Instead, after a journey of incomprehensible length, you would arrive right back where you started. The fate of a closed universe is as dramatic as the open universe is desolate. Its expansion would slow, halt, and then reverse. Gravity, the silent architect, would become the ultimate destroyer. Galaxies would cease their outward flight and begin a long fall back towards each other, accelerating into a final cataclysmic implosion. Everything would be compressed back into a single, infinitely hot and dense point, a big crunch, the perfect mirror image of the Big Bang. A story of cosmic rebirth, perhaps, but one of violent annihilation first. An open universe that expands into eternal darkness. A closed universe that collapses into a final inferno. Between these two dramatic fates, these two extremes of cosmic geometry, lies a third option. The perfect, improbable razor's edge balance. What if the universe contained the exact critical amount of matter and energy? Not too much, not too little. Just the precise density required to perfectly counteract its own expansion over infinite time. In such a universe, the fabric of space-time would have no overall curvature. It would be on the largest possible scales, perfectly flat. This is the geometry we know from our everyday lives. Here and only here do parallel lines remain parallel forever. The universe is infinite in extent, and it will expand forever, but only just. Its expansion will slow over eons approaching, but never quite reaching a complete stop. It is the ultimate cosmic balancing act. The fate of a flat universe is a gentle, fading elegance, a slow drift into quiescence. So, which of these three destinies is ours? Is our home a saddle, a sphere, or a sheet of cosmic glass? To answer this, scientists devised a way to measure the universe's total density. They created a single parameter, a cosmic measuring stick called omega. Omega is a simple ratio. It is the actual observed density of our universe divided by the critical density needed to make it flat. The entire fate of reality hinges on this one number. If omega is less than 1, our universe is open, its destiny a cold, lonely darkness. If omega is greater than 1, our universe is closed, doomed to collapse in a fiery big crunch. But if by some miracle omega is equal to exactly 1, if the amount of stuff in our universe perfectly matches that one sacred critical value, then our universe is flat balanced between oblivion and rebirth on a gravitational knife edge. For decades, astronomers worked tirelessly to take a census of the cosmos. They added up the light from all the stars. They calculated the mass of galaxies. They accounted for the vast clouds of interstellar gas. Then they added the mysterious unseen influence of dark matter and the even more baffling repulsive force of dark energy. They were building a cosmic ledger, trying to balance the books of reality itself. But their greatest tool for measuring the universe's shape would come not from looking at galaxies today, but by looking back in time to the very edge of creation. We can see the afterglow of the Big Bang. It is a faint, pervasive hum of microwaves that fills all of space, an echo of the moment the universe first became transparent to light some 3,800,000 years after its birth. This is the cosmic microwave background radiation, the universe's baby picture. And imprinted on this ancient light is a pattern of tiny temperature fluctuations, minuscule hot and cold spots that were the seeds of all future structures, including us. These spots have a characteristic predictable size. By observing them from Earth 13.8 billion years later, we can use them as a cosmic ruler to measure the geometry of the space they have traveled through. If the universe were closed and spherical, the curved space would act like a magnifying glass, making the spots on the sky appear larger than they really are. If the universe were open and saddle-shaped, the space would act as a demagnifying lens, making the spots appear smaller. But if the universe is flat, the light will travel in straight lines, and the spots will appear to us at their true, unaltered size. In the late 1992 and early 2000s, a series of increasingly precise experiments, from balloons floating high in the Antarctic stratosphere to sophisticated space telescopes, stared deep into this primordial light, preparing to read the universe's palm to tell its fortune. The world of cosmology held its breath. What would they find? Would Omega be zero? 3. A universe destined to fly apart? Or perhaps 1.5, a cosmos fated to fall back in on itself? Every plausible physical model suggested it should be one or the other. Perfect balance, perfect flatness, was a mathematical curiosity, a line with zero thickness separating two infinitely larger possibilities. To land on it exactly would be a coincidence of staggering proportions. The data came back, the analysis was checked and double-checked and checked again. The spots on the sky were not magnified, they were not diminished. They were exactly the size they should be if they had travelled across a perfectly flat canvas for 13.8 billion years. The measurement was undeniable. Omega is 1, not 0.99, not 1.01. To the highest precision we can currently measure, the density of our universe is identical to the critical density. We live in a flat universe. The cosmic spinning top is not wobbling. The celestial sculpture is not falling. Our universe is against all conceivable odds perfectly, exquisitely, impossibly balanced. And at this moment of profound discovery, a feeling of awe was quickly replaced by a creeping, chilling sense of dread. Because this isn't just a coincidence. It's a catastrophe for our understanding of the cosmos. Here is why this is a problem, a profound, deep intellectual crisis. This state of perfect flatness is what physicists call an unstable equilibrium. Think again of that pencil balanced perfectly on its sharpened tip. It is a state that is theoretically possible, but in practice utterly impossible to maintain. The slightest vibration, the gentlest air current, any minuscule imperfection, and it will inevitably catastrophically fall over. And once it starts to fall, it falls faster and faster. The same is true for the geometry of the universe. General relativity tells us that any tiny deviation from perfect flatness in the early universe should have been magnified exponentially over cosmic time. Flatness is like that pencil point. Openness and closedness are the stable, mundane states of the pencil lying on its side. If the universe had begun with even a sliver more density than the critical value, that extra gravity would have pulled things together slightly faster, making the universe even denser, which in turn would increase the gravitational pull, and so on. This runaway effect would have caused a universe that was almost closed to rapidly collapse into a big crunch long before stars or galaxies ever had a chance to form. Conversely, if the universe had begun with a fraction less than the critical density, its expansion would have quickly dominated. Space would have stretched so violently and so rapidly that matter would have been diluted to near nothingness almost instantly. The universe would be a virtually empty, barren void, incapable of forming a single star, for us to be here today in a 13.8 billion-year-old universe that still appears flat. The initial density at the dawn of time must have been tuned to the critical value with a precision that shatters the mind. The numbers are so absurd they almost lose their meaning. 1 second after the Big Bang, the density of the universe had to be equal to the critical density to an accuracy of 1 part in a quadrillion. That's 1 part in 10 to the power of 15. It is the equivalent of measuring the distance from the Earth to the Sun and being accurate to within the width of a single human hair. But that is nothing. If you go back even further to the earliest moments, physics can describe the so-called Planck time, a mere 10 to the minus 43 seconds after the Big Bang. The fine-tuning required is even more obscene. The value of omega then had to be equal to 1, to an accuracy of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. To write that number out, you would need more zeros than there are atoms in the entire solar system. This is not a coincidence. This is a cosmic conspiracy. It's like finding a single specific atom on a distant planet by firing a rifle from Earth and hitting it blindfolded. The universe should not be flat. The fact that it is a screaming, unignorable clue. It tells us that our understanding of the Big Bang as a simple explosion from a single point is incomplete. It is a message encoded into the very geometry of existence that something extraordinary, something violent and unimaginable happened in the first fraction of a second of our universe's life. Some unknown physical process must have seized the newborn cosmos and forced it into this state of perfect, impossible balance. It didn't just happen to be flat, it was driven to be flat. This perfect balance is not our universe's starting condition. It is a scar, a piece of evidence left over from a primordial event of unimaginable power. To solve the riddle of why our universe is so perfectly poised between life and death, we have no choice. We must follow this clue back in time, past the formation of atoms, past the birth of protons and neutrons. We must journey to the first trillionth of a second of existence. We must go in search of a theory that can account for this impossible precision. A search that will lead us to the very edge of physics, to a time before time itself, and to a radical idea that didn't just solve the flatness problem, but forever changed our vision of the cosmos, the theory of cosmic inflation. What if the longest journey you could ever take a voyage, lasting billions of years across the unfathomable darkness between galaxies, would eventually impossibly bring you right back to where you began? This isn't a riddle. It is one of the most fundamental questions we can ask about the nature of reality, a question whose answer is woven into the very fabric of existence. It is a question of geometry not on the scale of a classroom chalkboard, but on the scale of the entire cosmos. For centuries, we assumed that the space we inhabit was a simple passive void, an infinite and unchanging stage upon which the drama of stars and planets unfolded. We believed it followed the rules we learned in school, that parallel lines once drawn would march alongside each other forever, never meeting, never diverging. But this comfortable illusion was shattered by a revolution in thought that revealed space to be something far more profound. It is a dynamic entity, a substance that can be bent, stretched, and warped by the presence of matter and energy. And its overall shape, its grand cosmic architecture, holds the key not only to our ultimate origin, but to our final, inescapable destiny. Imagine for a moment a universe shaped like the surface of a sphere. Not a three-dimensional ball sitting in some higher space, but its four-dimensional equivalent, a cosmos that is finite in volume yet possessing no edge, no boundary you could ever reach. In such a universe, your journey would be the ultimate circumnavigation. Two beams of light fired in parallel from a cosmic torch would not travel alongside each other into infinity. Instead, their paths following the majestic curve of space-time would slowly, inexorably converge. Over billions of years, they would arc across the heavens to meet at a single point on the far side of creation, just as lines of longitude on Earth meet at the poles. This is what we call a closed universe. Its geometry is ruled by a gravitational pull so immense, so dominant, that the expansion we see today is merely a temporary phase. The initial energy of the Big Bang, the force that flung everything outwards, is ultimately insufficient to overcome the collective gravitational grip of all the matter and energy contained within. It is a universe living on borrowed time. The expansion will slow, it will halt, and then in a terrifying reversal it will begin to contract. Galaxies once rushing apart will reverse their flight, accelerating towards one another in a final cataclysmic homecoming. Stars will merge, the background radiation will heat to incandescent temperatures, and the entire cosmic structure will collapse back into the infinitely dense, infinitely hot singularity from which it was born. A big crunch. A universe with a beginning, a middle, and a definitive fiery end. It is a self-contained story, a cosmic jewel box, magnificent but ultimately doomed. Now picture a profoundly different reality, a universe whose geometry resembles the sweeping, elegant curve of a saddle. This is the open universe, a cosmos whose fabric is bent outwards, negatively curved. Here, our two parallel beams of light would suffer the opposite fate. Rather than converging, they would begin to drift apart their paths, diverging ever wider as they traverse the cosmic expanse. In this universe, the outward momentum of expansion is simply too powerful. The gravitational attraction of all the matter and energy is too weak, too diffuse to ever put the brakes on. This cosmos is not destined for collapse. It is fated for an eternity of accelerating loneliness. The expansion will never stop. It will continue forever, pushing galaxies further and further from each other until the light from our nearest neighbors can no longer reach us. The sky will go dark. Stars will exhaust their fuel and wink out one by one, leaving behind only the cold husks of white dwarfs, neutron stars, and black holes. Even these will eventually evaporate over timescales that make the current age of the universe seem like a fleeting instant. The result is a future of unimaginable cold and darkness, a big freeze or heat death, where the universe becomes a dilute, featureless soup of stray particles, its energy spread so thin as to be useless. It is a story without a final chapter, a promise of infinity that dissolves into a silent, empty void. One destiny is fire, the other ice. Both are born from the fundamental shape of space itself. Between these two dramatic apocalyptic fates lies a third possibility, a universe balanced on an impossibly fine edge. This is the flat universe. Here, the geometry is precisely what our high school teachers taught us to expect. Parallel lines remain parallel forever. The cosmos extends infinitely in all directions, just as we once naively assumed. In this reality, the outward push of expansion and the inward pull of gravity are in a state of perfect, exquisite equilibrium. The universe will continue to expand forever, but that expansion will slow down, continuously approaching but never quite reaching a complete halt. It is the cosmic equivalent of throwing a rock into the air with such perfect force that it escapes Earth's gravity, but only just its velocity, slowing to a near standstill as it drifts into the infinite distance. This flat universe represents the critical case, the dividing line between eternal collapse and perpetual runaway expansion. It is a universe defined not by cataclysm, but by an extraordinary precarious balance. For decades, cosmologists debated which of these three geometries described our home. Was our reality a finite closed sphere, a sprawling open saddle, or was it this perfectly balanced flat plane? The answer, it turned out, would depend not on theory alone, but on weighing the universe itself. The key that unlocked this profound connection between geometry and destiny was forged in the mind of Albert Einstein. His theory of general relativity, unveiled in 1915, was far more than a new law of gravity. It was a complete reimagining of the universe. He proposed that space and time were not a static backdrop, but were fused together into a single four-dimensional continuum space-time. And this space-time fabric was not rigid, it was active, shaped by the presence of everything within it. His famous dictum that matter tells space-time how to curve, and curved space-time tells matter how to move, was the revelation. Gravity was no longer a mysterious force acting at a distance. It was simply the consequence of objects following the straightest possible path through a curved dynamic geometry. A planet orbiting a star is not being pulled by an invisible tether. It is rolling along a valley in space-time, a depression created by the star's immense mass. A beam of light bending as it passes a galaxy is not being diverted. It is following the contour of the cosmic landscape. Suddenly, the universe's overall shape was not an abstract philosophical question. It was a physical property dictated by the total sum of all the matter and all the energy it contained. If you could somehow tally up every star, every galaxy, every wisp of gas, and every photon of light, everything that has mass or energy, you could calculate the curvature of space-time, and in doing so discover the ultimate shape and therefore the ultimate fate of the entire universe. For a time, Einstein and his contemporaries wrestled with this idea in the context of a static, unchanging cosmos. But in the 1920 seconds, another monumental discovery forever altered the landscape of this cosmic problem. Through the meticulous gaze of astronomers like Edwin Hubble, we learned that the universe was not static at all. It was expanding. Every distant galaxy we could see was rushing away from us, and the farther away they were, the faster they were receding. This was not an explosion of galaxies through a pre-existing space, it was the expansion of space-time itself. The cosmic fabric was stretching, carrying the galaxies along with it. This revelation infused the question of geometry with a new urgent dynamism. The shape of the universe was now intrinsically linked to a battle, a grand cosmic tug-of-war that has been raging for 13.8 billion years. On one side, you have the primordial, explosive energy of the Big Bang, the engine of expansion trying to fling everything apart. On the other side, you have the relentless collective gravity of all the matter and energy in the cosmos trying to pull everything back together. The ultimate fate of the universe, whether it closes, opens, or becomes flat, depends entirely on the outcome of this war. It all comes down to a single crucial number. This number has a name, the critical density. It is one of the most important concepts in all of cosmology. Imagine it as the universe's cosmic tipping point, the exact specific amount of mass and energy required per unit volume of space to perfectly balance the scales. If the actual average density of our universe is greater than this critical value, then gravity has the upper hand. There is simply too much stuff in the cosmos, and its collective pull will eventually overcome the expansion, leading to the big crunch of a closed universe. If the actual density is less than this critical value, then expansion wins decisively. There isn't enough matter to rein in the outward rush, and the universe will expand forever into the cold, dark oblivion of an open geometry. But if it is a monumental, if the actual density of the universe is precisely equal to the critical density, then we live in the extraordinary knife-edge reality of a flat universe. The cosmic scales are perfectly balanced. The expansion continues, but it is forever tamed, forever slowing in a state of sublime, perpetual equilibrium. Cosmologists represent this cosmic balance with a single Greek letter, omega omega. Omega is simply the ratio of the universe's actual observed density to the critical density. An omega greater than 1 means a closed universe. An omega less than 1 signifies an open universe. And an omega of exactly 1, that means our universe is flat. Finding the value of omega became the holy grail of observational cosmology for much of the 20th century. It was a quest to place our universe on the cosmic map of destiny. For decades, we tried to perform this cosmic census. Astronomers painstakingly counted galaxies, estimated their masses, and tried to account for the vast clouds of interstellar gas and the mysterious unseen dark matter we knew must be lurking in the shadows. For a long time, the numbers just didn't add up. The matter we could see, and even the dark matter we could infer, seemed to amount to only about 30% of the critical density needed for a flat universe, an omega of 0.3. This suggested we were living in an open, negatively curved universe destined for the big freeze. It was a plausible, if somewhat bleak conclusion, but then, in the late 1992, we found a new way to measure the universe's geometry, a method of unprecedented power and precision. By studying the faint residual glow of the Big Bang itself, the cosmic microwave background radiation, we could effectively see a snapshot of the universe as it was a mere 3.80000 years after its birth. Imprinted on this ancient light are tiny variations in temperature spots that were slightly hotter or colder than average. The apparent size of these spots as we see them today depends directly on the geometry of the space they have traveled through for over 13 billion years. If the universe were closed, space would act like a magnifying glass, making the spots appear larger than they really are. If it were open, space would act like a demagnifying lens, making them appear smaller. When we finally made the measurement with satellites like WMAP and Planck, the result was stunning, unequivocal, and utterly baffling. The spots were exactly the size they should be if their light had traveled through a perfectly flat geometry. Against all previous expectations, the measurements showed that omega is not 0.3, it is 1. To within a staggering precision of less than 0.5%, our universe is flat. The cosmic scales are balanced. And this is where a profound mystery, one of the deepest in all of science, opens before us. Because while a flat universe today is a remarkable discovery, it implies something about the dawn of time that is almost impossible to believe. The problem is this: The state of being flat is an incredibly unstable equilibrium. It's like trying to balance a pencil perfectly on its sharpest point. Any tiny deviation from perfect balance at the beginning will be massively amplified over time. The expansion of the universe acts as a powerful force that drives omega away from the value of 1. If the early universe had an omega that was even infinitesimally greater than 1, say 1, 0.000000000000001, the universe's curvature would have grown so rapidly that it would have recollapsed into a big crunch after only a few million years long before the first stars could even ignite. If, on the other hand, the primordial omega were just a sliver less than 1, for instance, 0.9999999999999, the universe would have expanded so violently and so quickly that the density of matter would have plummeted almost instantly. Space would have become an empty void, atoms spread so far apart that gravity could never hope to pull them together to form galaxies, stars, or planets. There would be no structures, no complexity, no life. Our very existence in a 13.8 billion-year-old universe that is still rich with structure is a testament to the fact that it did not begin in either of these ways. For our universe to be so close to flat today after billions of years of cosmic evolution pushing it away from flatness, its initial density at the moment of creation had to be tuned to the critical value with a mind-shattering, almost supernatural precision. To grasp the absurdity of this fine-tuning, consider this. 1 second after the Big Bang, the universe was a seething fireball of primordial particles. For it to evolve into the flat cosmos we observe today, its density at that moment could not have differed from the critical density by more than 1 part in a quadrillion. That is 1 part in 10 to the power of 15. It is a level of precision equivalent to measuring the distance from Earth to the nearest star Proxima Centauri and getting it right to within the width of a single human hair. But it gets even more unbelievable. If you go back further to the very earliest moments of cosmic time we can describe with our physics to the so-called Planck time, the required fine-tuning is even more extreme. The initial density of the universe had to match the critical density to an accuracy of 1 part in 10 to the power of 60. That is a 1 with 60 zeros after it. There are not enough atoms in our entire observable universe to write that number down. It is a degree of precision so immense that it beggars all human language and intuition. It is like firing a rifle from one side of the observable universe to the other and hitting a single specific proton on the first shot. Why? Why was our universe born with this impossible life-giving balance? Is it the greatest, most improbable coincidence in the history of existence? A cosmic lottery ticket with odds so astronomical they defy comprehension? Or is this extraordinary flatness not an accident at all, but the signature of some deeper, undiscovered law of nature, a mechanism that was at play in the universe's first fiery moments that forced the geometry of space-time into this perfect, life-permitting state? This is the flatness problem, and its resolution will take us on a journey to the very edge of space-time and scientific understanding. By the dawn of the 1970 seconds, a quiet confidence had settled over the halls of cosmology. For the first time in human history, we held in our hands a coherent, mathematically elegant, and observationally tested story of creation. The Big Bang model was not just a hypothesis, it was a triumph, a monumental intellectual edifice built upon 3 colossal pillars of evidence. It was a story that wound the great cosmic clock backwards from the familiar galaxies of today to a moment of unimaginable origin. This was not mythology. This was physics, a grand symphony of prediction and confirmation that seemed to have solved the ultimate question. The first pillar was the very one that had launched the entire revolution, the expansion of space itself. We had seen it in the starlight of distant galaxies. Their lights stretched and reddened as the fabric of space-time between us and them continuously unfurled. This cosmic exodus, the universal flight of galaxies away from each other, was the foundational observation. The model took this reality and imbued it with profound meaning. It wasn't an explosion times in time-space, but an explosion times of time-space. Running the film in reverse, the implications were inescapable. If everything is flying apart now, then long ago everything must have been closer together. Farther back, closer still. Until you reach a point of convergence, a moment of infinite density and temperature, a singularity from which all of space, time, matter, and energy erupted. This was the model's breathtaking starting point, and the cosmic expansion we see today is its ongoing magnificent echo, the lingering momentum of that singular genesis. But a great story needs more than a dramatic opening. It needs corroborating evidence. The second and perhaps most powerful pillar arrived, not with a thunderclap, but with a persistent, unexplained hiss. It was a faint, ever-present hum of microwaves, a whisper of static from every direction in the sky with no discernible source. Astrophysicists at Bell Labs, Arno Penzias and Robert Wilson had stumbled upon the oldest light in the universe. It was the afterglow of creation itself, the faint residual heat of the Big Bang's fireball. This cosmic microwave background, or CMB, was the model's smoking gun. The theory didn't just allow for such a relic, it demanded it. It predicted that the inferno of the young universe, once opaque and searingly hot, would eventually cool enough for light to break free and travel unimpeded through space. As the universe expanded over billions of years, that first ferocious flash of light would have cooled and stretched its wavelength, shifting from searing gamma rays down through the spectrum to the cool, placid microwaves Penzias and Wilson detected. It was a fossil, an echo imprinted on the sky. When we look at this light, we are looking at a snapshot of the cosmos when it was a mere 380000 years old, a celestial infant. And the most astonishing thing about this baby picture, its uniformity. The temperature of this ancient light is almost perfectly the same everywhere we look, a constant 2.725 Kelvin, whether we point our instruments to the north, south, east or west. This thermal equilibrium was seen as a resounding confirmation of the model, a sign that the early universe was a smooth, well-mixed primordial soup, just as the theory suggested. It was a whisper from the dawn of time, and it was telling us a story that perfectly matched our equations. The third pillar solidified the model's status from a compelling idea to a quantitative science. It addressed a fundamental question: why is the universe made of the stuff it's made of? Why is there so much hydrogen and helium and so little of everything else? The standard Big Bang model offered a startlingly precise answer. It proposed that in the first few minutes of existence, when the entire cosmos was hotter and denser than the core of our sun, it functioned as a universe-sized nuclear furnace. This was the era of Big Bang nucleosynthesis. It was too hot for atoms to exist, but it was the perfect cauldron for forging the nuclei of the lightest elements. For a brief, critical window of time, protons and neutrons fused together, cooking up the elemental ingredients that would one day form stars, planets, and us. The model made stunningly specific predictions. It was a cosmic recipe. Take 1 part initial conditions, bake for 3 minutes at 1 billion degrees, and you should end up with a universe that is roughly 75% hydrogen, 25% helium, with trace amounts of lithium and other light elements. And when astronomers pointed their telescopes to the oldest, most pristine gas clouds in the universe, sampling the material least contaminated by later stellar processes, what did they find? A universe made of 75% hydrogen and 25% helium. The numbers matched. They matched with breathtaking precision. This was the model's masterstroke. It didn't just paint a picture, it did the math. It connected the physics of the atom with the history of the cosmos, and it got the answer right. With these 3 pillars, the observed expansion, the CMB's afterglow, and the correct primordial element abundances, the Big Bang model stood as one of the greatest intellectual achievements in human history. The case seemed closed. But in science, a closed case is often just a door to a much larger, more bewildering room. The very success of the model, the very precision of its predictions, and the observations that confirmed them began to reveal deep, unsettling cracks in its foundation. The story was beautiful, it was elegant, it was confirmed by evidence, and yet it seemed to depend on a set of initial conditions so absurdly, so miraculously perfect that it felt less like a theory and more like a cosmic conspiracy. physicists began to feel a growing sense of unease, a suspicion that their triumphant theory was missing a crucial part of the story. The model explained how times the universe evolved from its first second onward, but it was utterly silent on times why. Times the universe began in such a profoundly strange and fine-tuned state. Two major paradoxes emerged from the data, two phantom inconsistencies that haunted the standard model. They became known as the Flatness Problem and the Horizon Problem. The Flatness Problem, the very subject of our journey, arose directly from the geometry of space we explored earlier. Remember omega, the cosmic density parameter that dictates the ultimate fate and shape of our universe. If omega is greater than 1, you have a closed universe, a sphere that will one day collapse. If it's less than 1, you have an open, saddle-shaped universe that will expand forever, growing colder and more dilute. And if omega is precisely exactly 1, you have a flat universe. A universe balanced on a knife's edge, a perfect Euclidean plane extending to infinity. This is the universe we see. Our best measurements today tell us that omega is astonishingly close to 1. Our universe is for all intents and purposes perfectly flat. In the 1,970 seconds, this wasn't just a curious fact, it was a terrifying one. Because according to the equations of general relativity that underpin the Big Bang model, a flat universe is an unstable state. Think of it like balancing a pencil perfectly on its sharpened tip. The slightest nudge in any direction, a tiny bit too much matter or a tiny bit too little, and the pencil will inevitably fall over. Cosmic geometry behaves in the same way. If the early universe had an omega that was even infinitesimally greater than 1, that deviation would have grown exponentially over 13.8 billion years. Gravity would have compounded on itself and the universe would have collapsed back into a big crunch billions of years ago, long before our sun even ignited. Conversely, if omega had been infinitesimally less than 1, that deviation also would have grown wildly. The universe would have expanded so violently and rapidly that matter would have thinned out to almost nothing. Galaxies, stars, and planets would have never had the chance to form. The cosmos would be a cold, empty, desolate void. Neither of these scenarios happened. We are here in a mature, richly structured universe, living on a planet orbiting a stable star in a vast, sprawling galaxy. This simple fact, our own existence, tells us that our universe did not fall off the razor's edge. It remained balanced. For it to be so exquisitely flat today, for omega to be so close to 1 after 13.8 billion years of cosmic evolution, its initial value must have been fine-tuned to an impossible degree. How impossible? The calculations are staggering. 1 second after the Big Bang, the value of omega must have been equal to 1 to an accuracy of about 15 decimal places. That's 1. Let that sink in. It is a degree of precision that shatters our intuition. It's like measuring the distance from New York to Los Angeles and being accurate to within the width of a single human hair. It's like throwing a dart across the entire Milky Way galaxy and hitting a single specific bacterium. The standard Big Bang model offered no explanation for this. It simply had to assume this miraculous initial condition as a starting point. It required the universe to begin its existence performing the most demanding, most improbable balancing act imaginable, and it gave no reason why. It was as if we had found a pencil standing perfectly on its tip for millennia, and our best theory could only say, well, it must have started out that way. This wasn't an explanation. It was an admission of ignorance. It was a fine-tuning problem of the highest order, suggesting that the cosmos we inhabit is not a typical outcome, but a statistical miracle of cosmic proportions. And as if this wasn't baffling enough, the second paradox was in some ways even stranger. It came from that beautiful uniform baby picture of the universe, the cosmic microwave background. The problem wasn't its existence, which was a triumph, but its uniformity, which was a paradox. Why should the temperature of the CMB be the same in every direction we look? At first, this seems simple. If you pour hot and cold water into a bathtub, you expect it to eventually reach a uniform temperature as the water molecules mix and exchange heat. This process is called reaching thermal equilibrium. The early universe we thought was like that bathtub, but there's a catch, a huge one. According to the laws of physics, information, and that includes heat, cannot travel faster than the speed of light. This sets a fundamental limit on how quickly different regions of the universe could have communicated or mixed to even out their temperatures. This limit defines a causal horizon for any point in space, a sphere of influence, the region of the cosmos that it could have possibly interacted with. Now let's look at the CMB again. Consider a spot of the ancient sky in one direction, say towards the constellation Leo. Then consider another spot on the exact opposite side of the sky towards Aquarius. When the light from these two regions was emitted 380,000 years after the Big Bang, those two patches of the universe were already separated by nearly 100 million light-years. Yet their light, when it finally reaches us today, reveals they had the exact same temperature down to 1 part in 100,000. Here is the paradox. There had not been nearly enough time since the beginning of the universe for a light signal or any causal influence to have travelled between them. They were outside of each other's causal horizons. They could never have been in contact. They could never have talked to each other, never exchanged energy, never mixed like water in a bathtub to smooth out their temperatures. And yet they are identical twins. It's not just those 2 points, it's every opposite point on the sky. It's like discovering 2 ancient isolated civilizations on opposite ends of the galaxy that without any possible contact independently developed the exact same language, culture, history, and even wrote the same epic poems word for word. You wouldn't just call it a coincidence. You would assume they must share a common origin, a past connection that you haven't yet discovered. The standard Big Bang model offered no such connection. It depicted a universe where these vast, causally disconnected regions simply emerged from the singularity with the same properties pre-programmed, with the same temperature from the very start. Like the Flatness Problem, the Horizon Problem pointed to an absurd level of fine-tuning in the initial state of the universe. It was another miracle demanded by the theory, another case of the cosmos starting off in a state of perfect, unexplained coordination. By the early 1980 seconds, the mood had shifted. The triumph of the Big Bang model was now tinged with a profound sense of crisis. The theory was like a brilliant detective who could flawlessly describe a crime scene, but had absolutely no idea how the conditions for the crime were set up in the first place. It worked perfectly, but only if you were willing to accept a set of starting conditions that were fantastically improbable. It explained the bang, but not what set the bang in motion so perfectly. Cosmologists were faced with a choice. They could either accept that the universe was simply a brute fact, a miracle of fine-tuning that we had no right to question and answer, many scientists found deeply unsatisfying. Or they had to accept that their triumphant standard model was fundamentally incomplete. There had to be more to the story. There had to be some physical process, some new chapter in the first moments of creation that could naturally explain this flatness and this uniformity. A mechanism that could force the universe onto its razor's edge path and allow its distant regions to coordinate their properties. The beautiful, successful theory of the Big Bang was not wrong, but it was clear it was not the whole story. It was a magnificent second act, but the universe, it seemed, was desperately in need of a new opening scene, and so we found ourselves at an intellectual impasse. We had stared into the heart of the cosmos and discovered a portrait of impossible precision, a universe balanced on the razor's edge of existence. The twin paradoxes of flatness and horizons were not mere scientific curiosities. They were profound contradictions, deep cracks in the very foundation of our understanding of cosmic origins. The Big Bang, our most triumphant theory, had led us to a place of untenable coincidence. It told us times the universe began, but it could not explain why times it began this way, so exquisitely fine-tuned for life, for structure for us. For decades, cosmology was haunted by these ghosts of improbability. The universe we saw simply should not be. It was as if we had found a single grain of sand balanced perfectly on its tip, and were forced to conclude it had simply landed that way by chance. Science demanded a better answer. It demanded a mechanism, not a miracle. The answer, when it came, did not arrive from the grand observatories gazing out into the cosmic dark. It emerged not from the study of galaxies, but from the arcane world of particle physics, from the mind of a young researcher at Cornell University named Alan Guth. In 1979, Guth was not trying to solve the riddle of the universe's shape. He was grappling with a more esoteric problem concerning hypothetical particles called magnetic monopoles, relics, predicted by grand unified theories. These theories suggested that at the extreme energies of the early universe, the fundamental forces of nature, except for gravity, would merge into a single unified superforce. The math worked beautifully, but it came with a frustrating prediction. The Big Bang should have produced a deluge of these magnetic monopoles, so many that they would dominate the mass of the universe. Yet we have never detected a single one. Where had they all gone? It was in wrestling with this puzzle, in exploring the physics of a supercooled high-energy vacuum state, that Guth stumbled upon something extraordinary. He discovered a side effect, a consequence of the equations so bizarre and so powerful that he at first struggled to believe it. He had found a trigger for a kind of cosmic hyperacceleration, a brief, astonishing moment when the universe could have been driven by a form of anti-gravity. He called it inflation. The name is deceptively simple, almost mundane for a process of such cataclysmic and world-altering violence. It describes a period beginning perhaps a mere 10 to the minus 36 seconds after the Big Bang, when the fabric of space-time itself underwent a mind-shattering exponential expansion. This was not the stately decelerating expansion we see today. This was a geometric detonation. In this infinitesimal sliver of time, a fraction of a second so small it has no meaning in our everyday world, the universe is thought to have doubled in size at least 100 times over. Imagine a single bacterium in the blink of an eye swelling to the size of the entire Milky Way galaxy. The scale of this event is so far beyond our intuition that language itself begins to fail. In that fleeting instant, a patch of space smaller than a single proton was explosively magnified until it was vastly larger than the entire observable universe we see today. It was a cosmic trumpet blast, an outburst of creation that set the stage for everything that would follow, fundamentally rewriting the first chapter of Genesis. Guth realized in a moment of electrifying insight that this one single event conceived to solve a completely different problem might just be the master key that could unlock cosmology's deepest paradoxes. Let us return to the flatness problem, to that cosmic knife edge where the universe's density omega sits so perfectly at the critical value of 1. The standard Big Bang model offered no reason for this. It was an initial condition we had to accept as a brute fact. But inflation changes the game entirely. It doesn't require the universe to times begin times perfectly flat. It could have started with almost any conceivable curvature. Imagine the primordial universe not as a smooth, perfect sphere, but as a tiny, intricately crumpled and wrinkled ball of foil. It could be wildly curved, folded and creased on the smallest scales. Now imagine grabbing that ball of foil and in a fraction of a second, stretching it out until it is the size of North America. If you were an ant living your entire life on a square inch of that now vast sheet of metal, what would you perceive? From your limited vantage point, your world would appear perfectly, flawlessly flat. Any wrinkles or curves that were present at the beginning would have been stretched out to such colossal scales that they would be completely undetectable within your horizon. This is precisely what cosmic inflation does to the geometry of space-time. It is a violent geometric uncrumpling of the cosmos. During that period of exponential expansion, the universe expanded by a factor of at least 10 to the power of 30 and perhaps vastly more. Any initial curvature the universe possessed, no matter how extreme, was stretched and diluted into near oblivion. Inflation acts like a cosmic steamroller, flattening the topology of space on a scale so grand that our observable portion of it appears to be a perfect Euclidean plane. It doesn't just make a flat universe likely, it makes it virtually inevitable. The theory transforms the flatness problem from an issue of miraculous fine-tuning into a simple, elegant consequence of early universe physics. Omega is not 1 because of a lucky cosmic roll of the dice. Inflation actively times the value of omega towards 1 with mathematical force. Like a gravitational gyroscope, it seized the chaotic curved geometry of the newborn cosmos and spun it out into a state of sublime and expansive smoothness. The flatness of our universe, once a source of deep philosophical anxiety, was now recast as the most predictable outcome imaginable. It was the first stunning victory for Goethe's audacious idea, but the triumph did not end there. Inflation's explanatory power reached even further, turning its attention to that other profound mystery, the horizon problem. How could opposite sides of the sky, separated by nearly 28 billion light-years today, share the exact same temperature to within 1 part in 100,000? These regions, according to the standard Big Bang model, have never been in causal contact. They are strangers separated by a chasm of space-time so wide that no light, no heat, no information could ever have crossed it in the entire age of the universe. Their thermal equilibrium was an impossibility, a message from 2 isolated islands written in the same ink, with the same handwriting telling the same story. It defied the fundamental law of physics that a cause must precede its effect. Inflation offers a breathtakingly simple and powerful solution. It proposes that, before the inflationary epoch began, the region of space destined to become our entire observable universe was microscopically small. It was a tiny subatomic patch, far smaller than the distance light could have travelled in that first fleeting instant of time. In this primordial crucible, everything was causally connected. Every point in that patch was in intimate thermal contact with every other point. There was ample time for this nascent cosmos to settle into a state of uniform temperature and density, like a drop of ink diffusing perfectly throughout a thimble of water. It was a smooth, hot, homogeneous quantum soup. Then the trigger for inflation was pulled. This tiny uniform region, this cozy neighborhood of space-time, was seized by the exponential expansion and flung apart with unimaginable velocity. 2 points that were once nestled side by side were suddenly propelled to opposite ends of the newly formed cosmic horizon. They were torn from causal contact, destined to travel for billions of years on diverging paths, unable to see or signal one another, but they carried with them a shared memory. The uniform temperature we see today in the cosmic microwave background is not a miracle of spontaneous coordination across impossible distances. It is the echo of a forgotten intimacy. It is the imprint of an era before the Great Expansion, a fossilized record of a time when everything we can see was part of a single, unified and perfectly mixed whole. Inflation doesn't violate causality, it reframes it. The distant regions of our universe look the same, because they were times the same, born from the very same microscopic patch of the primordial vacuum. The theory single-handedly dismantled the horizon problem, transforming it from a paradox into a prediction. The homogeneity of the universe was no longer an ad hoc assumption, but a direct and necessary outcome of the physics that ignited the cosmos. This is the hallmark of a truly revolutionary scientific idea. It doesn't just add a new detail, it rearranges the entire picture, making sense of disparate facts in a single, elegant stroke. Alan Guth's theory, born from the esoteric world of particle physics, had provided a coherent and physically motivated narrative for the universe's most perplexing features. It explained why the universe is so vast, why it is so flat, and why it is so uniform. It even explained the absence of those troublesome magnetic monopoles, as the inflationary stretching would have diluted their density so thoroughly that we would be lucky to find a single one in the entire observable cosmos. The intellectual shift was seismic. For the first time, cosmologists had a prequel to the Big Bang. The standard model had always started at a moment of infinite density and temperature, a singularity beyond which the laws of physics broke down. Inflation offered a glimpse into the mechanics of what might have happened just before the hot, dense phase we call the Big Bang truly began. It suggested the universe didn't just appear from nothing in a fiery state, but rather emerged from a dramatic phase transition in the fabric of the vacuum itself. It was a paradigm shift, elevating cosmology from a descriptive science, one that catalogued what it saw, to a predictive one, capable of explaining times why, times the universe possesses its fundamental characteristics. The idea was radical, and for many, it seemed like science fiction. It posited an era of physics so extreme, with energies so high that we could never hope to replicate them on Earth. It invoked a new undiscovered field, the inflaton field, to drive the process, a hypothetical entity whose properties were still largely unknown. The The theory was a beautiful, compelling story, a mathematical masterpiece that solved cosmology's deepest problems with stunning efficiency. But science requires more than elegance. It demands evidence. A theory, no matter how beautiful, is merely speculation until it can be tested against observation. And so the question that hung in the air, that echoed through the halls of academia and the control rooms of observatories, was clear and urgent. If this stupendous universe-forging event really happened, did it leave behind any fingerprints? Was there a fossil, an echo, a subtle whisper buried in the fabric of space-time that could prove this incredible story was true? The search for that proof would become one of the great scientific quests of our time, a journey that would take us back again to the faint ancient glow of the cosmic dawn, seeking the subtle signatures of that first cataclysmic moment of creation. It was a breathtaking, almost outrageous idea. A single hyper-accelerated instant, expanding a subatomic speck into a universe vast beyond all reckoning, neatly solving the puzzles that had plagued cosmology for decades. The theory of inflation was beautiful, it was elegant, and it possessed a terrifying, compelling logic. But was it science, or was it merely a brilliant mathematical fantasy? A story we told ourselves to make the cosmos fit our equations? A theory, no matter how exquisite, is worthless without proof. And the challenge facing cosmologists in the late 20th century was monumental. How could you possibly find evidence for an event that lasted for less than a trillionth of a trillionth of a trillionth of a second and happened nearly 14 billion years ago? There are no fossils from that time, no geological record. The event itself would have erased any trace of the universe that came before it. The search for a smoking gun seemed for all intents and purposes impossible, and yet there was one place to look. A single astonishing relic from the dawn of time, an artifact that permeates all of existence. It isn't hidden in some remote corner of the heavens. It is everywhere. It is flowing through this room, through you right now. It is the oldest light in the universe. We call it the cosmic microwave background, the CMB. To the untrained eye, it is just faint uniform static, a quiet hiss of microwaves coming from every direction in the sky, with a temperature of just 2.7 degrees above absolute zero. But to a cosmologist, this is no mere background noise. This is the afterglow of creation itself. It is a direct photograph of the moment the universe, at the tender age of 380000 years, finally became transparent. Before this moment, the cosmos was an impenetrable incandescent fog of plasma, a seething soup of protons and electrons where light was trapped, bouncing endlessly from particle to particle, unable to travel freely. Then, as the universe expanded and cooled, a great transition occurred. Electrons and protons bound together to form the first hydrogen atoms. In that instant, the fog cleared. The light trapped for millennia was suddenly set free, and it has been traveling across the cosmos unimpeded ever since. This ancient light is a messenger carrying with it a pristine blueprint of the infant universe. And crucially, it is not perfectly uniform, hidden within that near-perfect 7 Kelvin glow are temperature variations of infinitesimal subtlety, mere 100,000ths of a degree. These are not imperfections. They are the most important features in the entire cosmos. These tiny fluctuations in temperature correspond to tiny fluctuations in density in the primordial plasma. The slightly hotter, less dense regions would become the great voids of intergalactic space. The slightly cooler, denser regions were the gravitational seeds, the kernels around which all future structure, every star, every galaxy, every cluster of galaxies would eventually coalesce. We are here, you are here, because of those minuscule variations. They are the reason the universe is not a perfectly uniform, featureless, and utterly boring expanse of hydrogen gas. This cosmic afterglow, therefore, was the ultimate witness. And inflation, its proponents argued, had made a very specific, testable prediction about the nature of these fluctuations. The theory posited that these variations were not random. They originated as quantum jitters in the vacuum of space-time itself, impossibly small fluctuations that were then stretched by the violent expansion of inflation to astronomical scales. Think of the surface of a perfectly still pond. Inflation is like a colossal stone dropped into its center, sending out ripples. The cosmic microwave background is a snapshot of those ripples frozen in time. Inflation predicted a very specific statistical character for these ripples, a pattern known as a nearly scale-invariant spectrum. This meant the ripples should exist across all sizes, from small to enormous, with roughly the same intensity. Finding this signature would be strong circumstantial evidence. But there was an even more direct test, a way to use these ancient ripples to measure the very geometry of the space they traveled through. The largest, most prominent ripples in the CMB have a characteristic size, a preferred wavelength, determined by the physics of the early universe. We can calculate with incredible precision how large these features should have been back when the light was first released. By observing them today, 14 billion years later, we can see if they match. Imagine drawing a 1-meter line on a sheet of paper. Now look at that paper through a powerful magnifying glass. The line appears much larger. Look at it through a lens that makes things smaller, and it appears tiny. The actual size of the line hasn't changed, but the geometry of the space you are viewing it through the lens has distorted your perception of it. The largest fluctuations in the CMB are our cosmic measuring stick. If the universe were positively curved like the surface of a sphere, it would act like a cosmic magnifying glass. Those ancient ripples would appear larger in the sky than they should. If the universe were negatively curved like the surface of a saddle, it would act like a minifying lens and the ripples would appear smaller. But if and only if the universe were geometrically flat, if its total energy density was precisely equal to the critical density, would those ripples appear to us at exactly their true calculated size? The answer to the flatness problem was therefore encoded in the sky, written in a language of temperature and light. All we had to do was build a telescope sensitive enough to read it. The first major step came in 1992 with NASA's Cosmic Background Explorer satellite, or COBE. It gave humanity its first blurry baby picture of the infant universe, confirming that the fluctuations were indeed there. It was a Nobel Prize-winning discovery, a monumental achievement, but COBE's vision was too crude, its resolution too low to perform the definitive geometric test. It could see the ripples, but it couldn't measure their characteristic size with enough precision to distinguish between a flat universe and one that was only gently curved. For that, we needed a new generation of eyes, a mission designed with a single audacious goal to create the ultimate map of the CMB, a portrait of the infant cosmos so sharp, so rich in detail that it would redefine our place within it. That mission was the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, WMAP was not an ordinary telescope. It was an exquisitely sensitive differential radiometer designed to measure the minute temperature differences between different points in the sky. To escape the confounding microwave noise of Earth, it traveled 1.5 million kilometers away to a gravitationally stable point in space known as the second Lagrange point, or L2. There, shielded from the glare of the sun, the Earth and the moon, it began its silent, patient vigil, slowly scanning the entire sky over and over again. For years, the scientific community held its breath. The data streamed back to Earth, a torrent of numbers to be cleaned, calibrated, and painstakingly assembled into a coherent picture. The process was fraught with challenges, accounting for the interfering microwave glow from our own Milky Way galaxy and other foreground sources. Then, in February 2003, the first results were released to the world, and they were stunning. The WMAP image of the sky was one of the most important images in the history of science. It was an intricate, mesmerizing tapestry of hot and cold spots, red and blue splotches woven across the celestial sphere. It was the sound of the early universe made visible, a cosmic symphony frozen in time. And when scientists analyzed the data, when they measured the statistical properties of those spots and plotted them on a graph, the result was breathtaking. They performed what is known as a power spectrum analysis, which essentially sorts the ripples by their size on the sky and measures the strength of the signal at each size. The resulting curve had a series of peaks and troughs, the acoustic harmonics of the primordial plasma. The position of the very first and largest peak in that graph was the money shot. It corresponded to that characteristic fundamental wavelength, our cosmic measuring stick, and its position was unequivocal. The data showed that the largest ripples in the CMB were on average about 1 degree across on the sky. This was the exact size predicted with stunning accuracy for a universe with a perfectly flat geometry. It was not the magnified signature of a closed spherical universe. It was not the shrunken signature of an open saddle-shaped one. It was the pristine, undistorted signature of a flat, critical density cosmos. The case was for a moment seemingly closed. Inflation, the wild theory of a hyper-accelerated youth, had made a concrete, falsifiable prediction about the geometry of spacetime, and WMAP had delivered the verdict. The universe was flat. The theory had passed its most critical test with flying colors. It was a triumphant moment, a validation of an entire generation of theoretical work. We finally understood why our universe hadn't immediately collapsed back on itself or flown apart into a cold, empty void. It was balanced on a knife's edge because in its first ferocious instant, it had been inflated to a state of almost unimaginable flatness. But science is a relentless engine. Confirmation is never the end of the story. It is simply the beginning of a deeper level of questioning. WMAP was revolutionary, but could we do even better? Could we push the limits of precision to see if this perfect flatness held up under the most intense scrutiny imaginable? The European Space Agency answered this call with the Planck satellite launched in 2009. If WMAP had provided a high-resolution photograph, Planck was designed to deliver the ultra-high-definition full-sensory experience. It was equipped with detectors cooled to within 1/10 of a degree of absolute zero, making it vastly more sensitive than WMAP. It could see smaller features, measure temperatures with greater accuracy, and do a better job of filtering out the contaminating glow of our own galaxy. Like WMAP, it traveled to the L2 point and began its own meticulous survey of the sky. The world watched, wondering if Planck would find some subtle deviation, some crack in the inflationary paradigm. When the Planck data was finally released in 2013, the scientific community was once again left in awe. The new map of the CMB was a masterpiece of cosmic cartography, revealing the primordial fluctuations with astonishing clarity. And its measurement of the universe's geometry was so precise it bordered on the absurd. Planck confirmed WMAP's finding but crushed the remaining uncertainties. The universe, it declared, was flat to a precision of within 0.4%. This is a staggering level of flatness, equivalent to measuring the entire observable universe and finding it deviates from perfect flatness by less than the width of a single human hair. The triumph of inflation seemed absolute. The theory had not only explained the flatness problem, it had predicted the geometry of the cosmos with an accuracy that was now observationally verified beyond any reasonable doubt. It was one of the greatest successes in the history of physical science. And yet within this spectacular confirmation lay the seeds of a profound new mystery, a puzzle far deeper and stranger than the one inflation was designed to solve. The extraordinary precision of the WMAP and Planck missions did more than just measure geometry. It allowed cosmologists to conduct the ultimate cosmic census. By analyzing the detailed properties of the CMB fluctuations, the relative heights of the different acoustic peaks, they could determine not just the total amount of stuff in the universe, but precisely what kind of stuff it was. They could create a complete inventory of the cosmic budget, the recipe for our universe. And the results of that census were deeply, profoundly unsettling. First, they tallied up all the ordinary familiar matter. The atoms that make up stars, planets, gas, dust, and you. Everything we have ever seen, touched, or interacted with. All of it combined accounted for a shockingly meager 5% of the total energy density needed to make the universe flat. Next, they accounted for the dark matter. This is the mysterious, invisible substance whose gravitational influence we see holding galaxies and galaxy clusters together. It is the invisible scaffolding upon which the visible universe is built. Planck's data provided the most precise measurement ever made of its abundance. Dark matter, the census showed, makes up another 27% of the critical density. So we have 5% ordinary matter and 27% dark matter. That brings the total to 32%. But the universe is flat. Its geometry, confirmed with exquisite precision, demands that the total density be 100% of the critical value. This leaves a gaping hole in the cosmic budget. A staggering 68% of the entire universe was simply missing. Or rather, it wasn't missing. It was something else entirely. Something that doesn't clump together like matter, something that we had no name for, something that was smoothly distributed throughout the entire fabric of space. The data from the CMB, the relic of the hot, dense early universe, was screaming that the overwhelming majority of the cosmos today consists of a bizarre anti-gravitational energy, a phantom force driving space itself apart. This was the grand paradoxical twist. In our quest to confirm the theory that solved the flatness problem, we had spectacularly succeeded. Inflation did it. But the very data that proved the universe is flat also revealed why it is flat today. It isn't just matter and dark matter balancing the books. The scales are only balanced because the dominant component of our universe is this mysterious, pervasive dark energy. We had traded one cosmic fine-tuning problem for another, perhaps even more baffling one. We no longer had to ask why the universe began so perfectly flat. Inflation had answered that. Now we are faced with a new, more urgent question. What is this phantom energy that constitutes more than 2/3 of all reality? And what does its unnerving dominance mean for the ultimate fate of everything we know? The solution to one great mystery, had it turned out, only served to unlock the door to an even deeper, darker enigma. And so, a theory of exquisite power, born from the need to solve a puzzle of impossible balance, faced its ultimate trial. Inflation, for all its mathematical elegance, for all its explanatory grace in smoothing and flattening our cosmos, had to offer more than just a compelling backstory. It needed to provide a testable prophecy, a unique, unambiguous prediction that could be sought, measured, and verified. If that first untamed moment of exponential expansion truly happened, it could not have been a gentle process. It would have been the most violent event in cosmic history, an energetic outburst of such unimaginable scale that it would have violently shaken the very fabric of space-time itself. We had to ask, could we still feel the tremors of that cataclysm? The theory of inflation didn't just suggest we could, it insisted that the evidence must be there waiting for us. It predicted that this primordial convulsion would have generated a storm of gravitational waves, ripples in the geometry of reality, propagating outwards from the universe's singular moment of creation. These were not the waves from colliding black holes that our modern detectors now register, titanic as those are. These would be something else entirely, something far more profound. They would be the fossilized aftershocks of the Big Bang's initial blast, stretched by 13.8 billion years of cosmic expansion, until their wavelengths were now impossibly vast, spanning entire constellations. Finding them would be like placing a seismometer on the bedrock of existence and detecting the faint, lingering vibrations from the birth of time. But how could we possibly observe such an ancient and ethereal phenomenon? The waves themselves would be far too faint, too stretched, too attenuated by cosmic distance to be detected directly. Inflation, however, provided a crucial clue. It told us exactly where to look. The prediction was that these primordial gravitational waves, as they propagated through the infant universe, would have left an indelible mark on the oldest light in existence, the very light you've journeyed with us to understand the cosmic, microwave background. As this light, the afterglow of creation, began its long voyage, the rippling space-time would have squeezed and stretched the plasma of the early cosmos. This mechanical stress, this gravitational turbulence, would have been imprinted onto the light itself, encoded forever in one of its most subtle properties, not in its temperature, which we had already mapped with breathtaking precision, revealing the seeds of galaxies. No, this new clue, this smoking gun, was hidden in the light's polarization. Think of a light wave as a vibrating string. Usually light from a hot source like the early universe is unpolarized, meaning its waves vibrate in all directions, equally a chaotic jumble. But as this light scattered off electrons in the primordial fog, it would have picked up a degree of polarization, a preference for vibrating in a particular direction, much like light reflecting off the surface of a lake. Cosmologists had long predicted that the map of this polarization across the sky would contain specific patterns. These patterns, they calculated, would come in two distinct families named after mathematical properties known as E-modes and B-modes. The E-modes are beautiful radial or tangential patterns like the spokes of a wheel or circles around a central point. They are the dominant and expected signal generated by the simple scattering of light from dense, clumpy regions in the early plasma, the same clumps we see as temperature spots on the CMB map. They were a confirmation of our existing models, an important piece of the puzzle, and they were found exactly as predicted, but they were not the grand prize. The true treasure, the prophecy of inflation, lay hidden within the B modes. These are different. They possess a curl, a twist, a swirl. Imagine the lines of polarization forming tiny, elegant whirlpools across the sky. This specific twisting pattern, this celestial curlicue, cannot be easily created by the simple density fluctuations that form E modes. To generate a B mode pattern of this primordial type, you need something far more exotic. You need to physically twist the fabric of space-time itself. You need the unique corkscrewing strain that only a gravitational wave can produce. Finding a primordial B-mode signal in the cosmic microwave background would be the closest thing we might ever have to a direct photograph of inflation in action. It would be the echo of echoes, the light from the beginning of the universe twisted by the gravitational waves from the very first instant of time. The challenge was immense, the potential reward immeasurable. It was a signal so faint, so delicate, it would be like trying to discern the swirl from a single ship's propeller in the middle of an Atlantic hurricane. The search was on. To hunt for such a ghostly signal required a journey to the ends of the Earth. You cannot build a telescope for this kind of work just anywhere. You need the driest, clearest, most stable atmosphere on the planet to minimize interference from water vapor, which emits its own microwave radiation and clouds the faint cosmic signal. For this, humanity's most ambitious cosmological experiments have traveled to two of the most desolate places imaginable: the high arid plains of the Atacama Desert in Chile and the vast frozen expanse of the Antarctic Plateau. At the South Pole, an international team of scientists built a telescope with a singular purpose. They called it BICEP, the background imaging of cosmic extragalactic polarization. Stationed at the Amundsen-Scott South Pole Station, this instrument and its successors would stare unblinking at a single clean patch of the southern sky, season after season through the perpetual darkness of the 6-month polar night. Here at 2 miles above sea level, the air is so thin and so cold that it holds almost no moisture. It is the closest one can get to building a telescope in space without leaving the ground. For years, these researchers endured unimaginable isolation and extreme temperatures, often below -100 degrees Fahrenheit, to maintain and operate a machine designed to hear the whispers of creation. They were not just scientists. They were Antarctic explorers pushing the frontiers of human endurance in the service of the ultimate cosmological question. They were accumulating data year after year, patiently integrating the faint light from the dawn of time, building up an image of the polarized sky with a sensitivity never before achieved. The world of physics watched and waited. Then on March 17, 2014, the waiting ended. The BICEP 2 team, the second generation of the experiment, called a press conference at Harvard University. The atmosphere was electric. Rumors had been swirling for weeks, setting the scientific community alight with speculation. When the team presented their findings, the result was a bombshell. They displayed a map of their small patch of sky, and on it, clear as day, was a B-mode polarization pattern. It was not a subtle hint, not a marginal detection buried in the noise. It was a powerful, unmistakable signal with a statistical significance that left little room for doubt. The team had checked and rechecked their data, their instruments, their analysis for more than a year, trying to find any error that could explain what they were seeing. They could find none. They announced to the world that they had detected the imprint of primordial gravitational waves from the epoch of inflation. The room erupted. The news flashed across the globe. Here it was, the smoking gun. The discovery was hailed as one of the most important of the century, a Nobel-worthy achievement that seemed to close the book on the origins of our universe. Scientists on the panel were visibly emotional. Champagne was famously brought out. For a moment, it felt as though we had peered directly into the crucible of the Big Bang. The strength of the signal they detected was also a revelation. It was surprisingly high, suggesting that inflation was not just a brief, gentle affair, but an extraordinarily powerful and violent event, occurring at an energy scale that dwarfed even our most powerful particle accelerators. It hinted at a grand unified theory, the dream of physics that would unite the fundamental forces of nature. We had, it seemed, opened a direct window onto the physics of the first trillionth of a trillionth of a trillionth of a second of time. But in science, an extraordinary claim requires extraordinary evidence. And as the initial euphoria began to subside, other cosmologists around the world began to scrutinize the BICEP-2 result with the fierce collaborative skepticism that is the hallmark of the scientific method. Questions began to surface. The signal was indeed strong, but some thought it was times 2 times strong, stronger than the simplest models of inflation would have predicted. And while the BICEP-2 team had done heroic work in calibrating their instrument and analyzing their data, a formidable adversary remained an imposter that could masquerade as the very signal they sought. This cosmic villain was not some exotic new physics, but something far more mundane yet fiendishly deceptive: dust. Our own Milky Way galaxy is not empty. It is filled with vast, tenuous clouds of interstellar dust. These microscopic dust grains forged in the hearts of dying stars are not spherical. They are elongated like tiny needles, and critically they are aligned by the galaxy's sprawling magnetic fields. This alignment has a profound effect on the light that passes through them. As starlight and other radiation travels through these dust clouds, the aligned grains absorb and re-emit it, producing a faint microwave glow that is polarized. And because of the complex, swirling nature of our galaxy's magnetic fields, the polarization pattern this dust produces can have a curl. It can create B modes. The BICEP-2 team knew this, of course. They had chosen their patch of sky specifically because it was thought to be one of the cleanest, most dust-free windows onto the distant universe. They used the best available models of galactic dust at the time to estimate how much contamination they might expect, and concluded it was negligible. Their signal, they believed, was truly primordial. The debate hinged on one crucial question: did we really understand the dust in our own galactic backyard well enough to make such a definitive claim? The answer would come from space. While BICEP-2 had been staring deep into one small patch of the sky, another observatory, the European Space Agency's Planck satellite, had been doing the opposite. For 4 years, Planck had been patiently scanning the Time's entire time sky in 9 different microwave frequencies. Its primary mission was to create the ultimate high-resolution map of the CMB's temperature fluctuations, a task at which it succeeded brilliantly. But in doing so, it also created the most detailed map of galactic dust emission ever made. Planck was the ultimate dustbuster. It could measure the emission from these foreground clouds with unprecedented accuracy, and crucially, at multiple frequencies. This is because the signal from dust and the signal from the cosmic microwave background behave differently at different wavelengths. The CMB signal is what's known as a blackbody spectrum. It has a very specific, well-understood peak intensity. Dust emission, on the other hand, tends to get brighter at higher frequencies. By observing the sky in many different color bands, Planck could effectively fingerprint each source of microwave light and carefully disentangle the foreground from the ancient background. The BICEP-2 instrument, by contrast, observed at only a single frequency, making it much harder to distinguish between a cosmic signal and a dusty contaminant. The stage was set for a scientific showdown. The BICEP-2 team, with its deep, sensitive map of a small patch, and the Planck team, with its panoramic, multi-frequency view of the whole sky, decided to combine their forces. In a landmark of scientific collaboration, the two teams began a joint analysis, a painstaking process of cross-correlating BICEP-2's exquisitely sensitive map with Planck's definitive map of galactic dust. The tension in the cosmological community was palpable. Was the BICEP-2 signal real, a ghost from the dawn of time? Or was it a phantom, a wisp of local dust masquerading as a cosmic trophy? The answer, when it came, was a testament to the self-correcting nature of science. The joint analysis, published in early 2015, was conclusive. The swirling B-mode pattern that BICEP-2 had so clearly detected was consistent with being caused entirely by polarized dust within our own Milky Way. There was no room left for a primordial signal of the strength they had originally claimed. The initial triumphant announcement had been premature. It was a sobering moment for the team and for the field, but it must be understood this was not a failure in the conventional sense. There was no error in their instrument, no flaw in their primary data analysis. They had detected a real signal in the sky with incredible precision. Their mistake was an underestimation of the foreground, a misinterpretation of their signal's origin based on the incomplete dust models available at the time. The Bicep 2 saga was not a story of error but of process. It was science working exactly as it should. A bold claim was made. It was rigorously tested by the wider community. New data was brought to bear, and the initial conclusion was revised. In the end, the search for truth won out over the desire for a single spectacular discovery. And far from ending the quest, the experience galvanized it. The Bicep 2 result, even in its retraction, provided an invaluable lesson. It taught us that the foreground of our own galaxy is more complex and a more formidable barrier than we had ever imagined. It also placed a crucial upper limit on the strength of the primordial signal. If the gravitational waves from inflation exist, their signature must be fainter, more deeply buried in the noise and the dust than the Bicep 2 team had hoped. The hunt had just become much harder, but now we knew our enemy, and so a new generation of experiments has risen to the challenge, armed with the hard-won knowledge of the past. Experiments like the Simons Observatory and CMBS-4 are scaling up the effort on an unprecedented level. These are not single telescopes, but vast arrays of them deployed in the Atacama Desert and at the South Pole. They are designed with thousands, even hundreds of thousands of detectors each one, a technological marvel cooled to a fraction of a degree above absolute zero. They will observe the sky with the sensitivity of Bicep 2, but over much larger areas, and critically, at multiple frequencies simultaneously, just like the Planck satellite. This will allow them to create their own maps of the dust, to measure its properties with exquisite accuracy within their own observations, and to subtract its contaminating glow, cleaning the cosmic window with unparalleled precision. This is the cutting edge of observational cosmology, a monumental effort involving thousands of scientists from around the world. It is a slow, methodical, and painstaking search for a whisper beneath a roar. Inflation as a theory remains as compelling as ever. It is still the only idea that so naturally explains the flatness and uniformity of the universe we see around us. But its ultimate proof, the shimmering twisted light from primordial gravitational waves, remains tantalizingly out of reach. We have not yet heard the echo of the Big Bang, but we have built the most sophisticated listening devices in human history, and we are pressing them against the wall of creation. The search continues, pushing the boundaries of technology and our own persistence, driven by the profound need to know not just how the universe is, but how it truly began. And so the paradox finds its resolution. The cosmic ledger, which for so long seemed impossibly miraculously balanced, is finally understood not through chance, but through consequence. The flatness of our universe, that razor-thin line between eternal expansion and ultimate collapse, wasn't a condition set at the beginning of time with supernatural precision. It was forged. It was violently hammered into place by the single most transformative event in cosmic history, inflation. What began as a nagging inconsistency in our models, a quiet whisper that something was deeply wrong, has led us to a revelation that reshapes our entire conception of reality. We embarked on this journey to understand a single number omega, a measure of the universe's destiny. We sought to know why it was so astonishingly close to one. In finding the answer, we have done more than just solve a puzzle. We have been forced to confront the true scale of creation, the mechanism of our own genesis, and the startling possibility that our universe is but one of countless others. The search for balance has led us to the precipice of infinity. The power of the inflationary model lies in its breathtaking economy. It is not some complex, multifaceted contraption designed solely to solve the flatness problem. Instead, it is a key that unlocks multiple doors at once. With a single powerful push, that hyper-accelerated expansion driven by the energy of the vacuum itself, the cosmos is stretched, smoothed, and fundamentally reset. Any initial curvature the universe might have possessed, no matter how wild or dramatic, was ironed out, flattened to near perfection, just as the curve of a colossal balloon becomes indistinguishable from a flat plane if you are standing on its surface. At the same time, this same stretching mechanism solves the horizon problem, explaining why regions of the universe that have never been in causal contact share the same temperature. They were once intimately connected, nestled together in that infinitesimally small seed of a universe, before inflation flung them to opposite ends of the cosmos, forever bearing the imprint of their shared origin. It even sweeps the universe clean of exotic relics, like magnetic monopoles, diluting them to cosmic obscurity. A single, elegant idea resolves three of the most profound paradoxes in cosmology, a testament to its compelling power. It tells us that the universe we see today in all its balanced grandeur is the inevitable outcome of its own violent birth. This realization carries with it a profound implication. A perfectly flat universe where omega equals 1 possesses a strange and wonderful property. In such a cosmos, the positive energy bound up in all of matter and radiation is perfectly exactly cancelled out by the negative energy of gravity. The total energy of the universe is in a very real sense zero. Think about that for a moment. Everything you see, every star, every galaxy, every shimmering nebula, every living being, all of it is one side of a cosmic equation, and the relentless binding force of gravity is the other. It is the ultimate free lunch. It means our entire universe in all its staggering complexity and beauty could have burst forth from literally nothing, from a quantum fluctuation in a primordial void, without violating any known laws of energy conservation. The flatness of space is not just a geometric curiosity, it is the signature of a universe created from a state of perfect equilibrium, a magnificent structure built on a foundation of absolute zero. It is the architectural blueprint for a cosmos that can spring into existence without a cause, a self-contained system where all the accounts are perfectly balanced. This isn't just a mathematical quirk. It is perhaps the deepest insight we have ever gained into the nature of existence itself. Yet, as with all great scientific revolutions, the solution to one mystery serves only to illuminate the boundary of a much larger, darker unknown. Inflation provides a mechanism, but it does not explain the trigger. What was this mysterious inflaton field that possessed such astonishing anti-gravitational power? What gave it its energy, and what caused it to decay with such perfect timing, releasing its energy to create the hot, dense soup of particles that would become our Big Bang? These questions push us beyond the limits of our current physics, into a realm where quantum mechanics and general relativity must somehow merge. The inflationary epoch itself, lasting for a fraction of a second, took place under conditions of energy and density so extreme they are beyond anything we can ever hope to replicate on Earth. To truly understand it, we need a new theory, a quantum theory of gravity, a final chapter in physics that could describe the moment of creation itself. Inflation, the solution, has become the new frontier. It has given us a stunningly successful picture of what happened, a mere 10 to the minus 3, 6 seconds after the beginning, but the moments before that remain shrouded in the deepest mystery imaginable. We have read a spectacular chapter of the cosmic story, but we now realize it is not the first. This is where the story takes its most speculative and perhaps most awe-inspiring turn. According to many of our most advanced models, the inflationary engine once started may not have a simple off switch. The theory of eternal inflation suggests that while inflation ended in our pocket of space-time, allowing our universe to form and evolve, the process continues unabated in the vast expanse beyond our cosmic horizon. The inflaton field decays randomly, like pockets of steam condensing from a boiling cauldron. In this grander picture, our universe is just one of those condensed pockets, a single bubble in a seething, eternally expanding sea of cosmic foam. And in that foam, new bubbles, new universes are constantly being born. Imagine it a multiverse of countless, perhaps infinite universes, each one nucleating from the inflationary chaos, each one potentially expanding into its own vast cosmos. They would be causally disconnected from us forever, beyond our reach, their light never able to cross the eternally inflating abyss that separates us. We would be an island universe, in an infinite cosmic ocean. The implications of such a reality are staggering to contemplate. These other universes might not be mere copies of our own. The fundamental constants of nature, the values that govern everything from the strength of gravity to the mass of an electron, might be different in each bubble. The decay of the inflaton field in each region could settle into a different vacuum state, creating a unique set of physical laws. In one universe, gravity might be so strong that stars cannot even form before collapsing into black holes. In another, the electromagnetic force might be too weak for atoms to hold together. There could be universes with different numbers of spatial dimensions, universes made of particles we can't even imagine, universes so alien they would be utterly hostile to the very concept of structure or complexity. Our universe, with its specific life-permitting laws of physics, would be just one possible outcome among an infinity of others. Our reality would be but a single book with a unique story in a library that contains every book that could possibly be written. This is no longer just cosmology. It is a vision that touches upon the deepest philosophical questions of our uniqueness, our purpose, and our place in the grand scheme of things. This idea of a multiverse provides a potential, if unsettling, answer to another profound puzzle that has haunted physicists and philosophers for decades: the problem of fine-tuning. We have learned that our existence hinges on a set of fundamental constants that appear to be exquisitely fine-tuned for life. If the strong nuclear force were just a few percent weaker, the universe would contain nothing but hydrogen. If the cosmological constant, the energy of empty space itself, were not incomprehensibly small compared to theoretical predictions, its repulsive force would have torn the universe apart before the first galaxies could ever form. And of course, there is the flatness problem itself. Had the initial density of the universe deviated from the critical value by even a minuscule amount, the cosmos would have either recollapsed into a fiery singularity in its first few moments, or expanded so rapidly that no structure, no stars, no planets, and no us could ever have coalesced. We seem to live in a Goldilocks universe where everything is just right. Why this seemingly impossible luck? One answer is that it was simply designed that way, an explanation that lies beyond the realm of science. But the multiverse offers another possibility, one rooted in statistics and probability. This is the anthropic principle. It suggests that if there is a vast ensemble of universes, each with randomly determined physical laws, it is no surprise that we find ourselves living in one of the rare ones that can support our existence. We are here to observe the universe's flatness and fine-tuning precisely times, because times it is flat and fine-tuned. In all the other universes where the conditions are different, there is simply no one around to ask the question. It's like asking why we find ourselves on a planet with liquid water and a breathable atmosphere. We are here because we are here. We won the cosmic lottery not because the lottery was rigged in our favor, but because there were an infinite number of tickets, and our existence is by definition proof that we hold a winning one. This is a humbling and perhaps disquieting thought. It replaces our sense of specialness with a sense of selection. We are not the sole intended creation. We are the survivors of a cosmic Darwinian process on a cosmological scale. Our entire reality might be the product of a statistical inevitability, and so our journey comes full circle. We began with a deceptively simple question: why is the universe so perfectly balanced? We stared at a number omega and felt the deep unease of cosmic coincidence. That single question has acted as a powerful lens, forcing us to peer deeper into the first moments of creation than ever before. It led us to a theory of exponential expansion, a cosmic reset button that not only flattened space but also laid the very seeds of the structures we see today. The quantum fluctuations stretched to galactic scales that would one day become the great clusters of galaxies. It has shown us that our entire universe could be a zero-sum game, a magnificent structure born from nothing. And it has opened a door onto a conceptual landscape, more vast and more profound than anything our ancestors could have dreamed of, the possibility of an infinite multiverse, a place where our entire cosmos is just one bubble in an endless, creative foam. The flatness problem, that once intractable puzzle, has become a gateway to a grander understanding. It has driven us from a picture of a single unique creation to a vision of a potentially infinite, diverse, and eternal meta-universe. We do not have all the answers. We may never know for certain if these other universes exist. We are still searching for the definitive evidence of inflation, the primordial gravitational waves that would be its smoking gun. The new questions raised are as profound as the one we set out to solve. But that is the nature of science. It is not a destination. It is a relentless, ever-advancing journey into the unknown. We are a species defined by our curiosity, driven to look at the sky and ask not just what is there, but why it is the way it is. The flatness of our universe is more than a geometric fact. It is a clue, a message, from the first fraction of a second of time, telling us that the story of our cosmos is far stranger, far grander, and far more awe-inspiring than we ever dared to imagine. The perfect balance we see is not a sign of an ending of a finished work. It is the signature of a spectacular beginning, one that continues to unfold around us, and the invitation to keep asking questions, to keep exploring, and to forever be humbled by the magnificent, mysterious, and exquisitely balanced cosmos we are privileged to call home. The quest for knowledge continues, forever expanding, just like the universe itself.